Imagine hiring a senior engineer, right? You hand them this incredibly complex problem, and you watch them spend hours writing a brilliant, like 300-line Python script to parse some specialized database.
Sounds like a pretty standard Tuesday.
Right. They run the script, they solve the problem perfectly, and then right before your eyes, they just instantly delete the file from their hard drive.
Oh, man. That would be completely absurd.
It sounds absurd, but that is exactly how today's most advanced large language model agents treat the code they write. Welcome to AI Paperslop. Our mission is to cut through the noise and break down the most impactful AI research papers for you, the machine learning engineers and researchers in the trenches.
Yeah, we read the heavy stuff so you don't have to.
Exactly. Today, we are diving into a paper from researchers at ByteDance and RIT. It's dated May 27, 2026, and it's titled MUSE-Autoskill, Self-Evolving Agents via Skill Creation, Memory Management, and Evaluation.
It is a massive read, honestly.
It is. So here's the core 60-second summary for those of you building agentic pipelines. We know current LM agents are highly capable at reasoning through React loops.
Yeah, reasoning and acting, they do that great.
But they treat their generated skills as disposable, one-off code snippets. This paper introduces MUSE-Autoskill, which is an architectural framework that gives agents a unified 5-stage lifecycle for skills.
And those stages are creation, memory, management, evaluation, and refinement.
Right. So by equipping the agent with built-in sandbox testing, adaptive DAG-based context compression, and dedicated skill-level memory, MUSE doesn't just, improve baseline accuracy.
No, it goes way beyond that.
It actually generates skills that beat human-authored benchmarks, hitting an 87.94% success rate on achievable tasks.
Which is just a crazy number when you think about it.
It really is. And most importantly, these skills are externalized assets. You can literally drag and drop them into entirely different models, like Hermes, to instantly boost their zero-shot performance.
Yeah, and to really appreciate the necessity of this paradigm shift, we have to evaluate where the current state-of-the-art just hits a wall.
Right, because the community knows monolithic model weights aren't enough anymore.
Exactly. The ML community has broadly accepted that for complex multi-step engineering or data analysis tasks, agents absolutely need to use external tools.
We saw early breakthroughs in this domain with systems like Voyager, right?
Yeah, Voyager was huge. It successfully built an executable code library that allowed an agent to compound its knowledge over time.
But the issue with Voyager is that it was heavily constrained to the Minecraft environment.
Right. It didn't easily generalize to, real enterprise software environments. So we've seen subsequent systems like Autoskill and SkillsBench attempt to generalize that tool creation process.
Anthropic even released their agent skills format, specifically to standardize how we package these tools. But looking at systems like Autoskill, you realize the ecosystem still basically treats agent tool use like single-use plastics.
That is the perfect analogy. It really is.
You give the agent an objective, it burns serious inference compute generating a script, and then that script just vanishes when the session context window closes.
Poof, gone.
Why is it so fundamentally difficult to make an agent just remember a Python script it wrote yesterday and apply it to a new problem today?
Well, the barrier isn't a storage problem, Saving the raw text of a script to a database is trivial.
Right, storage is cheap.
Exactly. The difficulty lies in the fact that for a piece of code to be genuinely reusable across different tasks, it must be externalized, testable, and capable of accumulating usage experience.
So it needs a lifecycle, not just a hard drive.
Yes, it's a lifecycle problem. Current methods suffer from a highly fragmented lifecycle. For one, there is this massive creation usage mismatch.
What do you mean by that?
Well, skills are often synthesized in an offline environment, totally separate from the runtime context where the agent actually encounters the error. On top of that, the generated skills are usually static and unvalidated.
Oh, meaning the agent just generates a block of code and assumes it works.
Exactly. There's no native unit testing built into the pipeline.
And even if you solve the testing issue, you still run into the context window problem.
Oh, the context bloat is real.
If an agent is constantly iterating on code, reading tracebacks, and storing older versions of scripts, flat conversation histories are going to inevitably overflow, right?
Yeah. That is the final major gap in prior methods. Standard React loops just append everything sequentially.
Which is fine for a chat, but not for software engineering.
Right. During long horizon tasks, the context bloats so rapidly. And human software engineers don't operate like this. We write code, sure, but we also write dedicated test suites.
Right. We log specific bug reports. we patch the code incrementally.
Exactly. And we maintain documentation on its edge cases over time. Current LLM agents simply lack the underlying infrastructure to do anything resembling that.
Which brings us directly to the MUSE architecture. The authors frame their solution as giving the agent a complete 5-stage lifecycle.
Creation, memory, management, evaluation, and refinement.
Yeah. So to understand how this works, we need to look at the anatomy of a skill within the MUSE system. It is not just a flat Python file.
No, it's an entire directory structure. It actually draws heavy inspiration from Anthropic's agent skills format.
Okay, so what's in the directory?
At the root, you have a skill.md file, which serves as the primary interface for the model. Then you have subdirectories.
Like a scripts folder for the executable code.
Yep, a scripts folder, a resources folder for auxiliary data, and crucially, a tests directory.
Wait, a tests directory?
Yeah, built right in. And that directory structure fundamentally changes how the agent operates.
Okay, so walk me through the workflow. The master agent is running its React loop, right? Reasoning and acting.
Right. And eventually it hits a roadblock where its baseline tools simply aren't enough to, say, parse a specific file or execute a complex calculation.
So what does it do?
At that point, the agent utilizes a specific tool called SkillCreate. It passes a high-level specification of what it needs to a dedicated subagent called the skill creator.
Okay, so the master agent delegates the coding.
Exactly. And this subagent doesn't just write a single script. It synthesizes that entire directory package we just described, including the unit tests.
But hold on. If an agent is just writing its own code to solve a problem it inherently doesn't know how to solve yet, it is highly likely to hallucinate. Right?
Oh, absolutely. It might hallucinate logic or use completely incompatible libraries.
Right. And if it deploys that hallucinated code directly into the active environment, it's going to crash the task and pollute the entire session state.
And that is the exact vulnerability the evaluation and refinement stages are designed to eliminate.
Oh, so it doesn't just run it live.
No way. Once the skill creator finishes generating that directory package, it does not hand it back to the master agent for immediate use.
What happens to it?
MUSE routes the entire package to a separate evaluator module. This evaluator takes the unit tests from that new test directory and executes them inside a secure, isolated sandbox environment.
Okay, so if the tests fail in the sandbox, it doesn't blow up the main task.
Exactly. If the tests fail, the system doesn't throw a fatal error to the user. It generates a detailed execution trace of the failure, analyzes the stack trace, and automatically triggers an update skill tool to patch the original code.
Wow. So it's an autonomous, closed-loop debugging cycle?
Yes. And only after the unit tests definitively pass inside the sandbox does the skill get registered into the persistent skill bank for the master agent to actually use.
That's brilliant. But running a closed-loop debugging cycle inside a sandbox, analyzing full execution traces, and continuously updating code.
It takes a lot of tokens.
Yeah, they must generate an absolute mountain of tokens. How does the agent orchestrate multiple rounds of unit testing without completely nuking its context window?
Well, the context management engineering is arguably the most elegant part of the MUSE paper. They solve the token bloat using a highly specific two-pronged architecture.
Okay, break that down for me.
It's multi-level memory and a directed acyclic graph, or DABO, context manager. Let's look at the memory first. Alongside the standard short-term session memory and long-term retrieval memory, MUSE introduces an entirely new layer called skill-level memory.
Skill-level memory. How does that work?
Whenever a skill is successfully executed, the framework updates a hidden .memory.md file attached specifically to that skill directory.
So it's like a localized repository of usage history.
Exactly. It catalogs edge cases and lessons learned across different tasks without cluttering the master agent's primary context window.
It's essentially a developer diary for the skill itself. The agent is leaving a note for its future self saying, like, be careful, this PDF parser times out if the target file is over 100 megabytes.
That's a perfect analogy. And that specific insight is only loaded when the skill is actually invoked.
That makes so much sense.
Right. But the heavy lifting for the active session, however, is handled by the DAG context manager.
Because flat lists of messages just don't scale.
Exactly. Instead of a flat list, the conversation history is structured as a graph of nodes. Each node represents a distinct React turn containing the plan, the action, and the observation.
Okay. And as it loops, this chain grows.
Yep. MUSE monitors the token count and applies 2 levels of adaptive compression. Level 1 is single node compression.
So what triggers level 1?
If an individual node exceeds 15,000 tokens, which happens all the time when a tool returns a massive log dump or database query, MUSE performs an in-place summarization of just that specific node.
Got it. So it keeps the essential data and discards the noise. It acts like a highly sophisticated garbage collector for the KV cache.
Exactly. It isolates the token-heavy observations and shrinks them down.
But what happens when the sheer number of React turns starts to add up over a long task and level 1 compression just isn't enough anymore?
Then we hit level 2. When the total context size threatens to exceed the 180,000 token threshold, MUSE triggers level 2 compression.
And they set that threshold to leave a safe 20,000 token headroom for their GPT 5.5 backbone model, right?
Yeah, exactly. So level 2 is known as chain compression. The system takes a contiguous span of intermediate React turns and merges them into a single synthetic summary node.
Wow. So it encapsulates the logic of those combined steps.
Right. But it always strictly pins the first 5 turns and the last 5 turns of the session.
Oh, that makes sense. That pinning ensures the agent never loses sight of its original system instructions or the immediate working context of its current action.
Exactly.
Wait, though. If the system span merges intermediate turns into a synthetic summary, aren't you permanently destroying the exact step-by-step reasoning it might need later?
I see what you're saying.
I mean, summaries are inherently lossy, right? What if it needs a precise tool output from an hour ago?
They are lossy, which is why the implementation of the DAG is so critical. MUSE utilizes immutable history prev and history next pointers between the nodes.
Oh. So the data isn't actually deleted?
No. The active linear chain that gets sent to the LLM's context window is compressed, yes.
Well,
But the full uncompressed graph of raw nodes is never mutated or deleted.
it just sits safely in the background memory.
Exactly. If the agent realizes the synthetic summary is insufficient and needs a granular detail, or if an engineer needs to pause the session and resume it 3 days later, it's all there.
So cross-session state persistence guarantees perfect replayability.
Yes, the original data is never lost.
Okay, so we have a theoretical architecture that can write its own code, sandbox test it, self-correct through traces, and manage its own token economy like an OS virtual memory.
That's pretty good on paper.
But theoretical elegance doesn't always translate to performance. Did they test this?
Oh, they tested it heavily. The authors evaluated this framework on SkillsBench.
Which consists of 51 complex Docker-isolated tasks, right?
Yeah.
Spanning science and engineering, data analysis, document processing, and ops.
Right. They measured baseline agents powered by the same GPT 5.5 model. The vanilla MUSE agent, running without access to any external skills, hit an accuracy of 53.19%.
This is basically a coin flip.
Yeah. But when they equipped it with a library of human-authored skills scripts meticulously written by the benchmark designers themselves, the accuracy jumped to 68.4%.
Okay, so it beat other agents like Codex and Hermes at that point.
It did. But the true inflection point of the paper is phase 2.
Ah, phase 2, the self-creation experiment.
Exactly. The researchers let the MUSE agent attempt the 51 tasks without any pre-existing skills.
And for the tasks it managed to solve using just raw reasoning, they allowed it to distill its successful trajectory into a new, reusable skill package.
Using that whole 5-stage life cycle we talked about, once it populated its own skill bank, they reran the benchmark using only those self-created skills.
And the accuracy on those specific 35 achievable tasks skyrocketed to 87.94%.
Yeah, almost 88%.
Hold on. Hitting 88% means an agent distilling its own trajectory is vastly outperforming a custom-written tool authored by the human benchmark designers.
It's wild, isn't it?
What exactly is the agent doing in his code generation that human software engineers are just missing?
So the researchers conducted a skill anatomy audit to isolate the variables, and the differences are honestly stark.
Yeah.
They compared the MUSE-generated skill.md interface files against the human-authored equivalents. The agent-generated files were 2.2 times longer.
Wait, really? Just way more verbose.
Yeah. The median human skill file was 146 lines of code and documentation. The agent-generated skill was 326 lines.
Wow. I guess humans inherently rely on shared context. We are lazy documenters.
We are so lazy. We leave failure modes implicit. We assume the user understands the underlying input schema, and we just skip over procedural edge cases.
And the agent does none of that.
None of it. It spells out exact, rigid input and output schemas. It outlines explicit failure modes and provides highly detailed step-by-step procedures for every possible branch of logic.
It leaves absolutely nothing to interpretation.
Exactly. It's writing the ultimate idiot-proof manual for its future self.
That is a fundamental shift in reliability.
Yep.
Building verifiability into the documentation by default completely changes the risk profile of deploying these agents.
And because that documentation is so rigorous, the agent makes significantly fewer semantic errors when retrieving and applying the skill in future tasks.
Did the audit find anything else?
Yes, actually. It revealed that 9% of the MUSE-generated skills included a fully populated tests directory with discrete unit tests.
And the human ones?
The human-authored skills included unit tests 0% of the time.
0%. So the agent is building in self-verification natively while the humans just skip it.
Pretty much.
But building an incredibly robust, deeply documented skill that only works inside the MUSE ecosystem is basically vendor lock-in, right?
You would think so, yeah.
If these skills are tightly coupled to MUSE's specific system prompts, internal logic, or unique DAG architecture, they are practically useless to the wider open source ML community.
Portability is the ultimate test of utility here for sure. But the paper provides strong empirical evidence that these skills are truly agnostic.
Really? How do they test that?
They conducted a cross-agent transfer experiment where they took the raw skill directories generated by MUSE and dropped them directly into Hermes.
Hermes is a completely different agent architecture. It uses different internal prompts, different context management, different tool schemas.
Exactly.
Let me guess. Because Hermes parses tool descriptions differently and doesn't have the same internal dot memory pipeline, the MUSE skills immediately cause execution format errors.
That would be the expected outcome with older frameworks, but the complete opposite happened.
Wait, really?
Yeah. Hermes' baseline accuracy without skills was 47.89%. When injected with the MUSE-generated skills, Hermes' accuracy immediately jumped to 58.40%.
Wow, that is a plus 10.51 percentage point lift, zero shot.
Yep. It closed 79% of the performance gap between the baseline Hermes and Hermes equipped with human-authored skills.
That's incredible. So this proves that MUSE isn't just updating internal hidden model state or overfitting to its own prompts.
Exactly. It is producing genuinely externalized, highly transferable software assets.
Okay, the portability is proven, but we have to look at the compute economics.
The token cost.
You're generating massive 300-line markdown files, running sandbox test environments, continuously updating code.
Sounds expensive.
Right. I mean, the prompt cache might absorb some of the static context, but injecting these massive skill.md files into the system prompt on every single React turn sounds like it would cause massive latency spikes and API cost overruns.
It would if they did it that way. But the token economics are actually incredibly favorable due to a mechanism they call catalog routing.
Catalog routing.
Yeah. The heavy body of the skill.md file is never blindly injected into the system prompt.
Oh, so it doesn't load the whole file up front.
Exactly. The active prompt only receives a tiny YAML catalog. This catalog consists solely of the names and brief one-paragraph descriptions of the available skills in the bank.
Okay, so when does the massive instructional body actually get loaded?
It's lazy loaded. It only enters the active context after the agent reads the YAML catalog and explicitly decides to execute a read skill tool.
That makes total sense. This architecture keeps the marginal token cost per turn exceptionally low, regardless of whether the agent has 10 skills or 1,000 skills in its bank.
Yep. The upfront token cost to generate the skill is high, but the amortized runtime cost plummets.
Do they give specific numbers on the savings?
They do. The paper notes that generating a skill in Phase 2 costs about 383,000 tokens as a one-time distillation event.
Okay, that's a decent chunk of change.
But once that skill is in the bank, utilizing it creates a Pareto optimal frontier for inference. Median latency drops by 273 seconds per task.
Wow, that's huge.
And total token consumption drops by 85,000 tokens per task.
Because instead of wandering through a long ad hoc React exploration chain, making mistakes, and querying the LLM dozens of times, the agent just calls the pre-vetted skill.
Exactly, and it solves the task in a fraction of the steps. Plus, roughly 58.5% of the input tokens for these loaded skills are absorbed by the API provider's prompt cache.
So you're getting a massive capability boost at a heavily discounted inference rate.
You pay the computational tax once during creation to guarantee efficiency and reliability for all future executions. It essentially shifts the compute burden from inference time to compile time.
It is clearly highly efficient once the skill is written. But wait, out of the 51 tasks in SkillsBench, MUSE failed to generate a skill for 16 of them.
Yeah, I didn't hit 100%.
Where does this architecture fundamentally break down?
Those 16 field tasks expose the primary limitation of the current framework, which the authors identify as the Phase 1 bottleneck.
What's the Phase 1 bottleneck?
Well, in order for MUSE to synthesize a skill, it first has to solve the task at least once zero-shot, using only raw React exploration.
Oh, I see. So if the agent simply lacks the fundamental knowledge to solve the task initially, it fails to produce a successful execution trace.
Exactly. Many of these failures involved highly obscure production tooling, like diagnosing complex Azure BGP routing logs or executing heavy numerical math involving partial differential equations.
So if the agent cannot stumble its way to a successful outcome, there is no trajectory to distill.
Right. It is a classic cold start problem.
It's a total catch-22. It needs to succeed at the task to write the skill, but it needs the specialized skill to succeed at the task in the first place.
And beyond the cold start problem, they also documented a slight regression issue in a subset of tasks due to overfitting.
Overfitting the skill itself.
Yeah. For example, in an HVAC control task that required tuning a proportional integral derivative controller, the agent successfully calibrated the PID loop and generated a skill based on that run.
But I'm guessing that code only worked for that specific run.
Exactly. The resulting code overfitted to the specific noise profile and calibration window of that single simulator instance.
So when the skill was applied to fresh runs with different environmental noise,
the tuned gains fell outside the verifier's stability margin, causing the simulation to crash. The agent encoded a rigid procedure that worked perfectly for the training instance but lacked out-of-distribution robustness.
So how do ML engineers break that catch-22 loop? If the agent fails the initial task, the whole pipeline stalls and it learns nothing about the environment.
Well, the researchers highlight a highly promising future direction, extracting diagnostic partial skills from failed trajectories.
Partial skills, like giving it credit for the parts it got right.
Essentially, yeah.
Yeah.
Even if an agent ultimately fails a complex engineering task, it might have spent 10 React turns successfully figuring out how to authenticate with a proprietary Azure database.
Or how to properly parse a heavily nested vendor log format.
Exactly. If the system can be trained to recognize and package those small intermediate victories into partial skills.
Or even learn explicit anti-patterns of what not to do.
Right. Then it could bootstrap its way up the complexity ladder, compounding knowledge even from its failures.
That is fascinating. We are witnessing a fundamental shift in how we conceptualize LLM capabilities. We're moving from a world where we treat agent actions as monolithic black box behaviors derived entirely from model weights,
to a world where agents are autonomously writing, testing, and managing externalized software infrastructure.
Exactly. By structuring tools as testable code with their own dedicated memory files, we are watching agents transition from being clever conversationalists to becoming actual software maintainers.
Which is a massive leap forward.
It really is. Which leaves us with a fascinating concept to consider as you build out your own agentic workflows. If models can now reliably generate sandbox tests and rigorously document their own reusable skill libraries.
And we know those libraries transfer perfectly to entirely different models.
Right. How long until we see a decentralized open source package manager for AI?
Oh, wow. Like a PyPI or NPM ecosystem, but built exclusively for agents.
Exactly.
Yeah.
A real-time repository where models autonomously publish, version control, and download verified skills from one another, compounding their collective intelligence across the entire internet without any human intervention.
That is a wild thought to end on.
It is. Thank you for joining us for this deep dive into the source material. We'll see you on the next one right here on AI Paperslop.